Very much. It's a great pleasure for me to introduce Soren Knudstorp from the University of Amsterdam. He's from the ILLC, and he was here already at Chapman back in November 2023 for a month. And in that month, he solved 2 open problems.
Wow.
Oh, wow.
And then he went back to Amsterdam, and these were long, standing open problems from like.
And now how many problems you solved?
Yeah. Then he went to Amsterdam and he solved another 2 open problems.
Wow.
And then he said, he'd like to come back
Yeah,
to Chapman.
And now,
Sure, come
now
back.
there are no more open problems.
Yeah.
So he could not solve either. There is no more. He solved it anyway.
This is very simple. In 1 month, he sort of solved 2 open problems at Chapman. And in how many months in Amsterdam?
More than a year.
Okay.
Ah.
So you're yeah.
But now he came for
This
2.
is obvious why you should come back.
Yeah.
And so in the time that he's been here, he's already solved another open problem.
See?
But we have plenty to go to get to the same rate of problem solving. We'll see how much we can do here, but it's an absolute pleasure to have you give this talk now. So please go ahead. Thank you.
Thank you so much, Peter. Thank you so much to all of you for having me here, not only for this talk, but also in general. It's been a pleasure. I've been here for almost 3 weeks now, really enjoyed it. And I'm sure I will also enjoy the next 5 weeks that will be here. Let me see. So I will talk about features of undecidable logics in this talk. And the plan for the talk is as follows. So wait, no, let me actually also just mention. So you have this handout. I will probably not use it a lot, but let me briefly just say what's about. The first part is this sort of translation. So sometimes I will talk about things algebraically. That's the notion you have on the right-hand side. And sometimes we'll talk about it, so here called in logic. I'm not sure if that's the right word, but like another word would essentially mean the same thing. They're just 2 different perspectives on the same objects. And then you also have some definitions, both on the first page and also on the page afterwards. I will probably not use it a lot, but you have it in case you want to look something up. There are some definitions recorded here. Okay, now back to the presentation. So the plan for the talk is the following. So first, I will talk a bit about undecidability. So don't despair if you don't know what it is. I will tell you the what and the why. Then I will talk about something called propositional team logics. And the reason I will be talking about this is twofold. So one is that I actually do quite a lot of research on propositional team logics. So I thought it would be nice to give you at least just a glimpse of what this is. Also given I'm going to be here for another 5 weeks. And the other more important reason is that it actually works as a gateway, as a nice introduction to start exploring these boundaries between the decidable and the undecidable, which will be the rest of the talk on the main part of the talk. What we'll be doing is that we'll be solving some problems and obtaining some insights, try to characterize some features of decidable or undecidable logics along the way. And at the end, we will use these features, use these insights to attack one final problem and solve it, and then also provide a new proof of a known result. Okay, so this is the plan for the talk. Of course, if you have any clarificatory questions, please feel free to come forward and let me know. Let's get to the first part, so undecidability. What is it and why is it interesting? So very briefly, you can define the notion of a decision problem, which is just a collection of inputs with a yes or no question for each input. So take a very boring but also illustrative example. Take the inputs to be the natural numbers and think of the yes or no question given a natural number. Is it prime or not? This is an example of a decision problem. Then we say that a decision problem is decidable if there's an algorithm, effective method, that given any input accurately answers the question. So for instance, the problem I just said, when you are given as inputs the natural numbers, and the question is this natural number?
Sorry.
Yes.
Here is apparently very clear, but in fact it's not. It depends on what you mean by algorithm. So here the simple question, is the action or choice a tool for deciding something?
So the notion here is formalized by Turing machines.
Yeah. So the action or choice is not a machine.
No, indeed. So so the notion of algorithm, the idea is, well, it depends on these things. You can also, there are parts of the action choice that are actually algorithmic, right? But that's another thing, like countable choice and these things. But no, so the idea is that we have this notion.
Algorithm is a Turing machine.
Yeah, indeed. Yeah, so the idea is that we actually have, but you can just think of it sort of informally as an effective method, a way to like have some sort of algorithm, and essentially this you can cash it out mathematically, but informal, this is just your sort of intuition of what it means to have this sort of mechanical procedure, step-by-step method.
And so that, just to be clear, so that means that the set I is something that can be encoded as.
Indeed.
As tape,
typically like natural numbers.
As inputs for a tape or something like that, right?
Yeah, exactly.
Binary strings or something.
Indeed.
And is it necessarily numerable? No. I is numerable necessarily?
Yes, it has to be. It actually has to be.
Yes.
Yeah.
They are
Otherwise,
independent decision one after the other.
Because if you took the real numbers or something like that, you can't
It
encode.
would be an logical machine, it would be, right?
What?
For real numbers or for no countable numbers, you have to use a kind of an analogical device.
Yeah.
It's not a Turing machine anymore.
Indeed.
I guess you can say that you also have an algorithm to detect whether something is or not part of I,
Yes.
Is or not?
whether it is or not an input.
Okay. So yeah, so the main idea is that we have this notion of the inputs, and then we say that our decision problem is then given such an input. Is it, and then we have this question, yes or no. For the example I gave before with the natural numbers and the question of parameters, this is indeed decidable because one algorithm could be given such a natural number. You just follow these instructions, check the natural numbers below it. There are only finally many. Do any of them divide your number? Any of the, like, that is not one of the number itself. If there's no algorithm, we say the problem is undecidable. So this is the idea of what it means for something to be decidable and undecidable. Our setting will be logical systems. And we say that a logic in a language is decidable if there is an algorithm that, given any formula of the language, this determines or decides whether it's actually validity, whether it's part of the logic.
Not whether
Otherwise,
it is a
it's
theorem or
undecidable.
not, whether it is part of the language.
No, so we say given any formula of the language, this is so our input is formulas of the language.
Okay.
And the decision
okay.
problem or the question we say, is it a validity? Or like is it a tautology, is it derivable or not? And then I just use this notation or something.
Okay. I did not see the difference between the two.
Oh yeah, it's also
Okay.
if there's no such, then it's undecidable. Okay, so now you know what this notion of decidability is and undecidability. But why would you be interested in this? Like, why is this interesting? I think there are many reasons for it. So one reason is that actually, if something is decidable, if you have an algorithm, then it can be implemented in a computer. It's very, like, for practical purposes, it can be useful. And you can say sort of vice versa, if you show something's undecidable, you sort of give some theoretical limits, at least to what you can practically hope to get out of it. This is one reason. I think it's a good reason. But it's not what drives me. What drives me is that consider the space of sort of all of these decision problems, of all of these problems. Then we have this conceptual distinction now. You can talk about those problems that admit a sort of mechanical algorithmic solution to them. And we can talk about those problems that don't, that fall outside of that, when they're non-mechanically solvable, non-computable. And I find this distinction to be incredibly interesting. So for me, why care about decidability or undecidability? Well, because this distinction is a deep and profound conceptual distinction. I find it at least to be. And this is what really drives me to explore this. Okay, so this was the what.
Please, sorry.
Yes.
I think that you will time to present one out for your paper, but at least we understand each other.
Yeah.
What you said, I found very, very interesting. But I don't think that in order to tell it that there is a profound conceptual distinction, you need to buy this very strange notion of totality of problems. Because I have the impression that totality of problems is something as a class. So something that is contradictory structure. Problem what they are. It is important to distinguish between what does it mean to be decidable, what does it not mean to be indecidable. So you can have an intentional approach to that rather than an extensional.
Indeed. It was only mostly, my idea was just like sort of by analogy, like think of it, even though like think of it at least. So there's a difference between how we conceptualize things and how we would maybe formalize them. And like conceptualize was just what I was thinking is think of this sort of conceptual distinction between things that are decidable. Yeah, in this way.
What I found out is you have a set that is the set of all the problems.
This was only a way to conceptualize it, but indeed one need not formalize it in that way in an extensional manner. It can be intentional for sure.
You get the point.
For sure. But the intentional distinction then between these things I find incredibly intriguing. Thanks. Okay, so this was the first, the undecidability, the what and the why. Now, I also promised and I said that we will talk a bit about these propositional team logics and in particular the decidability. So only give you a glimpse into what they are because my main focus is to go further and talk about decidability. But in a nutshell, if you want to understand propositional team logics, it's easily contrasted with the sort of semantical systems you know. So take things like classical propositional logic. The way you give semantics for them is that you evaluate formulas with respect to single valuations. The same in first order logic, right? In first order logic, you evaluate formulas with respect to single assignment functions, or in possible world semantics for modal logic, you evaluate formulas with respect to single possible worlds. Team semantics is just that you take this and evaluate with respect to sets of evaluations, sets of evaluation points. And this is what people call teams. That's why it's called team semantics. In particular, in the propositional setting, you evaluate formulas phi, not with respect to a single valuation B, but with respect to a set of such valuations. In a nutshell, this is the idea. Now, there are many reasons why people might study this. In particular, when you get to this setting, you can start introducing other sorts of vocabulary, other kinds of connectives that might be interesting for philosophical purposes, linguistic purposes, mathematical purposes. For now, let me just give you sort of a few of these clauses that people are considering. So the way you give the team semantic clauses, so you have to say, we now know we know that we are evaluating with respect to teams, but how are we actually evaluating with respect to teams? So let X be the set of propositional, set of valuation functions. Now for subset of such, so member of the power set of X, we define the following. So I'm gonna go briefly over them. It's not so important what they are, but I wanted to sort of have an intuition. So the first one is that we say that a set, so a team, satisfies or supports or makes true P, if and only if, right, it's a set of valuations. So when should it satisfy a propositional letter? Well, if all of the valuations in it actually satisfy it. I think this is a quite natural condition. And then the conjunction is as you know it. And then you have a clause here. So this is the inquisitive disjunction, it's called, which has this, and the semantic clause for it is the disjunction as you know it, but it's typically written using this other notation because it's used when people want to say what's the meaning of questions actually. And then you can think of this W as like whether, it's the W, whether something is the case, whether A or B, and so on. Then you have a negation, and then you actually have a second disjunction, which is usually used this more normal, more common disjunction symbol. And what it says is that a team satisfies a disjunction phi disjunction psi if and only if it's composed of something that satisfies one disjunct phi, something which satisfies the other disjunct psi, and it's the union. So it's composed by the union. So this is the clause that it's also called the split disjunction, because you can think of it as a team satisfies if it can be split into a phi part and a psi part. Okay, so these are some clauses. Don't dwell too much on them.
Sorry,
yes.
S is a team.
Exactly. So it's a set of valuations. It's a team, indeed. And that's why we can split and we can talk about
so
the
for the quantificator, for the quantifier for any V means on the element, for any element of S.
Exactly. Okay. So it's a set of valuations and we say
But the T does not remember the semantic of possible word for modal logic.
One more time?
The semantic of possible word for modal logic. One statement is necessary, one is true in all possible word. So it seemed to me that something similar to the notion of necessity, according to...
No accessibility relation.
There's no accessibility relation here, right? Or actually we'll come back to that in a moment.
No accessibility relation.
Because there's no diamond
It
above.
should be like a S5. A semantic for S5 could be, but not for S4 or K.
No, no, yes, yes, yes.
S5.
Yeah, there are definitely some similarities to that for sure. Actually, what you get is that if you take the fragment, okay, we don't have it right here, but you can get its conservative over classical logic if you have a bit of, if you add some other things. So it is true that you can see some notion of some, and classical logic, right, is sort of kind of like S5. Good McKinsey task translation, translate classical logic into S5, for instance. That's another story. Okay, so in any case, here we have the clauses.
The last clause could be also put with a universal quantifier, right? Is for all V in S, either be satisfied phi or satisfied phi.
Actually not. It would do if we had it in fragments of the language, it would work. But actually, when we have in particular the negation here and also this disjunction, actually you can't, it doesn't reduce. So the notion, it is inherently team-based and not based just on the actual
But if you have two
elements.
subsets that the union is the total thing, and then all the ones satisfy phi and all the others satisfy.
Yeah, but it's not. So the thing is that the clause you have for the atomic clause, right? That one doesn't live to arbitrary formulas, right? So we don't. And what I mean by this is that you don't have in general for arbitrary formulas that this holds here. All yes, this if and only if does not hold, and this.
Oh no, I mean the last clause, the disjunction.
Yeah, and because this doesn't hold this here, disjunction you cannot say that it's for all valuations in it. It satisfies phi or psi, right? Because if you take, because you don't have, if you had this if and only if in general, then it would hold, but you don't have that. So it's inherently actually based on, for fragments of the language, you will have this, but you don't have it in general. So it's really, the formula is really inherently based on the teams of the
I see.
information.
Because the negation is an existential.
Yeah,
It could
yeah,
be.
yeah.
Must S prime and S double prime be distinct?
No, they can even all be S. So if S just satisfies both phi and psi, then S is equal to S union S. Okay,
The two disjunctions are deeply different one to the other.
indeed. We'll get back to that in a moment. This is good. You're making some good observations. I will elaborate on them in a moment.
They're really two different things.
Yeah, we'll get to that. Okay, so but now I want to talk a bit about decidability. So first I want to make this observation that propositional team logics are decidable. And how do you make this observation? Well, what you do is that, so decidability, I have to exhibit an algorithm. Here's the algorithm. Give me a formula phi. Then look at that formula, find all of the propositional letters. Consider all of the valuations over the propositional letters. There are only finite many propositional letters or variables, as people also call it. So it means this set here is finite. That means that this power set is finite, so only finite many teams over it. And all you have to do now is actually just check the notion of validity, whether for each of these, which are finitely many, whether S actually supports phi. And this here shows actually decidability of it. But for me, this explanation is hardly satisfactory, to be honest. So why is it, or what is it that makes propositional team logic decidable while other logics are not decidable? Like, sure, I have a proof here, but it doesn't really tell me what is it, what feature of propositional team logics actually makes it decidable. Okay, in order to try to understand this, right now, the way that I diagnose...
I always believe that the answer is stupid, simply because it's very simple. No, it's much more deep.
It can actually be way more deep than that. I think.
Okay.
Yeah, indeed. And let's see. So let's try to do that. And the way we do that, show that it's actually deeper, is that we will try to take this team semantics, put it in a setting we understand better, and compare with other things. And what we're going to do is that first, we're going to look at these semantic clauses, as we did before. And then we're going to say, okay, so that first disjunction, the whether disjunction, the inquisitive disjunction, it's just a normal disjunction. Then we have the negation. It's also just a normal negation. And then we squint even harder and we see that this final disjunction, it is actually like a modality. So if you think of it, so if you know modalities from modal logic, a diamond, what it says, right? So something satisfies diamond phi, just in case it can access something else that satisfies phi. There exists something else that satisfies phi it can access. We have this here as well. It's just binary rather than unary. So we satisfy phi disjunction sign if and only if we can access two things that stand in this relation in terms of union. One satisfies phi, the other satisfies psi. So we're going to change this symbol to a circle. This circle is just a notion of a modality. Think of this just like a modality, binary modality.
So what is the difference than before?
No, the semantic clause is the same. I'm just changing vocabulary into something we know. So the right-hand side is all the same. Now I just rename these things because we can see that these are things we actually know. The first disjunction was just a
So the
disjunction.
double V now is V,
Yeah.
and the V is now is O.
Exactly.
So the original notation that you used was introduced by the team semantics people.
Yes, indeed. So this notation we had before is the team semantical notation, and now I'm like, I see a modal logic here. So I'm like, this here is just a disjunction, as it would be in modal logic, for instance. This all, and this here is just negation, and this here is actually just a binary modality. Okay, so now what we have here is that, okay, let's think about it. Say we have a team semantic model, so we have a team of evaluations, we have just these clauses here. Then this here induces a normal Kripke model, as we know from modal logic. So we have to say what the frame is. The frame now, it's a power set, right? So usually what you have a set and you have a relation on it. In this case, our set happens to be a power set. And then we have a relation on it. So it's a ternary relation. And that ternary relation is just the one induced by the union. And that's what the binary modality refers to. If it's a unary modality, it refers to a binary relation. Now it's binary modality, so it refers to a ternary relation, which is just a union. Okay, so this is the frame, but then the underlying model, we can also notice something, and that is that we have this clause for the propositional letters, right? And so the model here will be a model, so we have this frame here, but with a valuation that goes to these principal downsets, principal ideals, right? Because what teams I is it that satisfies a propositional letter? Well, it's exactly those members of the power set, so that everything in it satisfies P. Well, that's just the same as the downset of this, or everything that is below, everything that's a subset of this here. So whenever we have a team semantic model, it induces a Kripke model as we know it, but with a principal valuation. And in fact, this thing we're capturing now is even stronger. If we take, now we're going to define a logic in the Kripke style, take all power set frames. In this sense, we take a power set with a union on it, redefine the base clause to the completely normal one we know from modal logic, completely standard one, and then we have all of these things that are standard, but instead of taking arbitrary valuations, only allow for those principal valuations, those that go to principal downsets, principal ideals, those that go downwards. Then we get sound complete relational semantics for team logics. So like relational semantics, same as Kripke semantics, in terms of these relations. What's that?
Let me understand this equality of this line that says VP is equal to, this is a set of sets of X.
Exactly.
But how should I read the right-hand side? So what is this down arrow? What is selecting?
It says, so you take this here and then you take everything below it in terms of subset.
So you take the set of all the valuations that make P true.
Yeah.
And then you take all the other sets of valuations.
All the subsets of those.
All subsets.
So it's also just a power set actually.
Okay, that's the power set. Okay,
Yeah,
okay.
But the idea is that because we know, right, that you satisfy this if and only if all of your valuations say that you make it true. But that's just the same as saying you are a subset. This means I am a subset. I'm a subset of that one that contains all of them that make it true. So, okay, but in any case, the important, so then the proof, it's a simple polymorph, is not so important. The important part here is that we had our team semantic setting. Now we have rephrased it into a setting we might know better in terms of like modal logic or relational semantics. And we just have power sets as our frames with this notion of this union. And then we have this restriction on valuations, so they have to be persistent, they have to be downwards closed in this way in terms of the principle. Okay, so this is one way to phrase it. Now there's going to be an interlude. I also want to say, how can we think of this algebraically? So, okay, so that's the general idea that whenever you have a set A and you have some, in this case, ternary relation on it, then we can form its complex algebra. So we take a power set, instead of subsets, we take intersection, union, confrontation, and then we lift the ternary relation as follows. We sort of pointwise say that when we have two elements of our algebra, B and C, then B circle C is just those A and A, such that A is related to some B and some C from B and C, respectively. This is a standard way of forming complex algebras. Let me also say, if you're not familiar with algebraic semantics, what I'm saying now is an interlude. It's not important whether you follow it. Try to follow it because it's nice, but if you don't, it's okay. So this result here is a Boolean algebra with an operator. Or the result is, so we have a Boolean algebra, this power set, intersection is conjunction, R is the meet, etc. Okay, now in our case, the thing we are lifting, the set A is already a power set, and then the relation R is the union relation. So if we just give them some colors, what we actually do is that what we end up when we lift it is we'll have the power set of the power set. And then we will have that this notion here, the relation from before with the blue, will now just be the union. Okay, so this is what happens algebraically. Now, finally, let power plus denote the class of complex algebras of power set with union. So doing this here. Okay, so what is team logic? Team logic is the theory of this class of algebras where homomorphisms from the term algebra, so this is that your homomorphism, we only consider those homomorphisms from the term algebra that send variables to principal downsets.
And we could see it as a neighborhood symbol, right?
It is sort of similar to neighborhood semantics also, yeah.
I mean, with some kind of a bit of weird topology behind it.
Yeah, I think that definitely some similarities, yeah. So, okay, so, and then if we instead of only, so now we only take homomorphisms, so this is from the term algebra. If we allow for arbitrary homomorphisms, then what we would get is a variety generated by this sort of construction. Okay, but team logic is that we actually only consider those homomorphisms that go to these principal downsets, principal ideals. And we have this notion, right, because we're taking the powers of the powers. Okay, let us recap a bit. So summarizing team logics, they're decidable. 2, we can rephrase them. We can just think of them as cryptic semantics where our frames are just power sets with union, and where we only take those special kinds of evaluations that are principal or equivalent algebraically. So now this poses a question. We've rephrased this in terms of modal logic in this sense, or in terms of algebras in this sense. If we take the same signature as before, but what if we allow for arbitrary evaluations? So instead of having this restriction, we just take exactly the same things, but instead of having this restriction on the evaluations or restriction on homomorphism from term algebra, are we then decidable? Does the logic remain decidable? I think this is a natural question coming from here. And in fact, this question is also intimately related with an open problem, which is that if we consider, instead of taking power sets, right, we could just take arbitrary Boolean algebras. This is something that GALAI and GALAI they considered, and they raised the problem of this decidability.
What do you mean by carrier?
The carrier is so up here, so the power set frames, it's Boolean. Instead of having a power set, it's just an arbitrary Boolean algebra.
Okay. Thank you.
Yeah, no, very good question, yeah. Arbitrary Boolean algebra, then you can just think of the union as the join. You can also think of it as the mean, actually, that's not important. But you take that as your frame, and then you instead of taking power sets. Good question. Thanks, Ben. Okay, and here's the result. If we stop having these restriction evaluations, we become undecidable. The power sets are undecidable, also the Boolean algebras undecidable. So this will be the complex algebras of Boolean algebras also. This is something they call it hyperboolean modal logic, but you can just think of it as the modal logic of Boolean algebras, just like you think of the other one, the one with power sets, as the modal logic of power sets. Okay, now we have the theorem. What is the proof? I'm just going to give the sort of general method. So we want to prove something undecidable. So what we're going to do is we're going to interpret another undecidable problem within it, so that if we were decidable, then that other problem would be decidable, but we know it's undecidable. Okay, so, and the way we define it is that we define first the notion of a tile, for one tile, and that's just a square with a color on each side. So take, for instance, this one over here. So this is just a square. It has the color red upwards, green to the right, blue down, white to the left. Then we have to define the decision problem, right? And remember, the decision problem takes a set of inputs. Our set of inputs here is just a finite set of tiles. Could be these ones. And then we have to have this yes or no question for each input, so for each finite set of tiles, and that's just determine whether each point in the quadrant or in the plane can be assigned a tile such that neighboring tiles share matching colors on connecting sides. So indeed we want to have this sort of tessellation. Can we tessellate the plane of the quadrant using these? So if we have two tiles next to each other, we have to put them on all these points in the plane that next to each other. So if this one has the color red to the right, and then this one also have the color red to the left, and similarly up and down. This is the decision problem. It is in fact undecidable. So it was introduced by Wang Hao and proven undecidable by his student Berger, which I think, by the way, is also actually quite cool. This in and of itself, right? There's no algorithm, at least if we assume the Turing thesis, no effective method that given a finite set of tiles, you can check whether you can tessellate the plane. It's beautiful, I think, by the way. But in any case, so this what we'll use here is also that this problem here, we're using our proof. And what we do is the following. So for each finite set of tiles, we construct algorithmically, so a formula such that W tiles the plane if and only if it is not valid. Which is say, if and only its negation is not valid. If and only if it's satisfiable. Okay. Now we have two results, right? For the power set, the Boolean and the Boolean algebras. To catch both in one go, we derive the proof, this if and only if of the proof idea. So let me just say, if you have this proof, if this goes through, then you get undecidability, because then if you could have a decision procedure for the validity problem, you would in particular have it for the tiling problem. The tiling problem is undecidable. Okay, so we want to have this if and only if. Now we want to prove this if and only if for two different logical systems at the same time. And that we can do by taking this if and only if and just divide it into one direction each. So we say that, and then we prove like follows. So if this formula is satisfiable in a Boolean frame, then we can tile the plane, and vice versa. If we can tile the plane, then it is satisfiable in a power set. If we prove the lemmas in this way, then we get both results in one code. Right? So why do we get if and only if both of them? For Boolean algebras, we want to show this here. So if it is satisfiable in a Boolean frame, then it tiles it, that we have. And we have that if it tiles it, then it's satisfiable in the power set. But a power set is a particular kind of Boolean algebras. Vice versa, if you want to, why do we get the if and only if power sets? Well, so we assume that it's satisfiable in a power set, but a power set is a particular kind of Boolean algebra. And then we use this lemma. And vice versa, here we already get a power set there.
The first lemma is crucial for decidability. That's where you, by most tolerance, basically.
They are both crucial. You need both. You need the if and only if. Yeah, you need the if and only if. But it is indeed crucial.
I'll ask for it.
Okay, yeah. Okay, so let us take stock. So this was the proof. Now we have our first insight. We know that the team semantics, right, was where we had this restriction on valuations. But if we just disallow that restriction, we go from the realm of the decidable to the realm outside of the decidable, in the undecidable realm. So inside one, valuations do matter.
I'm sorry. The proof you showed us had to do with checking finitely many subsets.
Yes.
Now you don't have to check finitely many anymore, because otherwise it would still be decidable.
Indeed.
Where does the infinitely many come from?
So, okay, yeah, good question. So let us go back to this here. So the idea is that the way when we present the logic in this different way, then, so let's see, so here we have the logic here, right? So when we no longer have this restriction, so it's essentially this p-Morphism argument, when we no longer have this restriction, the idea is here, what we can do is that things, because we have principal downsets, somehow we can take equivalence classes of things, because they all just go down and like intersect in some way. But when you don't have that, when you have arbitrary evaluations, you don't have this notion of equivalence classes that can make it sort of finite. I can spell it out a bit more, maybe perhaps afterwards, but the intuition is really that this principal downset means that we can collapse many things. And when you don't have that restriction, then suddenly can be things below you and you don't know, like if you know you set for something here and something's below you, you know nothing about it basically. When you have the principal downset, you can say a lot. That's the intuition. See, so we were here. Then, okay. So there's also a new question, right? So now we talked about valuations. But think about this way, we had in the power sets and in Boolean algebras. So for power sets, it's undecidable. If we weaken the requirement and we take the broader class of Boolean algebras, it's still undecidable. Can we weaken even further and stay within the realm of decidability, or realm of undecidability? And in particular, if you weaken from power sets, which are specific instances of semi-lattices, we actually get a problem posed by Bergman, by Peter, and also by me. And this was actually the way the entry for me into this, and like, or at least one of the entries was that when I arrived here last time, Pete and I, we talked a bit about different things, and then we realized we had actually both been interested in this problem, among more things. And yes, even when we weaken to semi-lattices, we stay undecidable. For any class of semi-lattice containing this particular semi-lattice, its logic in the signature is undecidable. And the formulas that show this are in the handout. I think if you want, you can look at them. I'm not sure how interesting it is, but you have the definitions. In case if you're interested, there's also, I haven't published anything here, but the manuscript is available on request.
Is this connected to the pigeonhole principle? It's formula that, big enormous formulas that people use in Tableau to show that it is hyper, like a hyper exponential. It's a pigeonhole formula usually, right?
No, I don't think. It might be that I don't know enough about it to answer your question, but I don't see any relation to the pigeonhole principle.
Yeah, but Rachel said it's normals, conjunction and disjunction, like hyper exponential.
Yes, but I think but pigeonhole isn't, so that would be more within the decidability realm. You would use these arguments, no? Like to show like high complexity. And now we are outside, we're even more complex with the undecidability.
No, exactly. I mean, hyper, like a hyper exponential, but even sometimes even decidable, but in very hard domain. Well, there's a paper by Marcello D'Agostino which makes this distinction. We can.
Oh, would be nice. Yeah. No, thank you. Okay, so when we're in semi-lattice, we are. So if we go all the way from power set to Boolean algebras, even to semi-lattice, we're undecidable. So for instance, this shows also that the modal logic, because we get this theorem, right? It says we have this convex region, we have this interval. So also if you take the modal logic of lattices, distributive lattice, Heyting algebras, it's undecidable. Because those are particular kinds of semi-lattices that contain this particular semi-lattice. Now, what if we weaken even further than semi-lattices? So we have these our frames, our structures, we interpret them, power sets, to Boolean algebras, we can even go all the way down to semi-lattices. But what if we weaken even further? Now, I'm going to give you a partial answer, and later on I can tell you why it's sort of partial. So another way to construe semi-lattices is as partial orders, and that's not why it's a partial answer, with all binary suprema. So what we could do instead is we consider just the logic of all partial orders simpliciter. So instead of taking all partial orders with binary suprema, we take all partial orders suprema. No. Instead of taking all partial orders with all binary suprema, we just take all partial orders simpliciter. We don't have this restriction to only taking those that have at least our bounds. Then what you get is actually something called modal information logic, and this is decidable. Okay, so here we again have like if we can go all the way down to semi-lattices, but as soon as we sort of lose this restriction of having the binary suprema, then we get decidability. Otherwise, we're in the undecidable territory. Then you can also ask a different question, right? So essentially we've asked about the sort of the valuations of them, or the homomorphisms on them. Then we talked about the structures that generate it, so the frames. But we could also say, okay, let's look a bit at the language. Let's look at the signature. So if we let's stick to semi-lattices, as we were in before. But if you omit negation, so the signature is this, what we actually obtain is truth mega semantics. So finite truth mega semantics is also the same as FAST for those who know it. And for our purposes, this is decidable actually. Okay, so now we have some more sort of like trying to carve this boundary. We have some more insights. The first one is that associativity matters. And now you might be wondering, where does associativity enter the picture? And then the idea is that you can essentially think of the difference between partial orders and semi-lattices as the difference between whether you impose associativity or not.
So negation is a problem.
Also, that will be the next insight. But you're right, it's good. But first we take this insight, but very good. So, and the way to think of this, why does this associativity matter? How does it enter? So think of it, if you have a partial order, so I'm going to write you a partial order, where what we have here, so let's suppose, and now it's talking like as a cryptic frame. So suppose we have some point over here, I'm not going to write the name of the point, but it satisfies phi. This one satisfies psi. And then let's actually say we're also going to have this here. And this one here satisfies, I've forgotten how to write chi, I think it's like pi. Okay, now this point here, right, is the least over bound of these two. Least over bound of these two. So it satisfies when we are in this setting, right? So this is the notion of it satisfies this when you're the least over bound. Then this one here is the least over bound of this one here and this one here. So that means that this one here satisfies this formula, circle this formula. Okay, but it does not, and this is just a partial order, but it's not a similarity, and it does not satisfy this here. And why does it not satisfy this here? Because there's nothing that is the supremum of a psi and a chi. Because you have psi here, you have chi here. There are two overbounds that are incomparable. These 2 points don't have a least overbound. So partial orders, they're not associative. And you can conceptually, at least for this, sort of think of similarities as sort of imposing associativity. So at least for our purposes, it's close enough. Okay, so this was the first insight. We knew that we would go all the way down to similarities. We are undecidable. As soon as we lose this associativity in this and just take partial orders impliciter, we get decidability. Then we already have the next insight. Exactly, negation matters. If we're in similarities, if we get rid of negation, we become decidable. Okay, so we have gathered 3 insights. Let's now see if we can use these insights to attack a problem, one final problem. And that is a logic called the relevant S. So let's see if we can use our insights. So the problem of concern is that, is this relevant? So it's a relevant logic S. Is it decidable? It is, let me just explain what it is. So it's the logic of similar frames, but where you also have a bottom element, so a least element. Partial order with binary suprema, but also a least element. We have arbitrary evaluations. The signature is that you only have conjunction, disjunction, and implication. But this implication here is very much related to the circle we had before. So this notion of this modality, because it's actually the residual. So it's the residual, this one.
So it's the residual of fusion.
Of fusion, exactly, yeah. Okay, so what do we know about this problem? So we know that if you omit disjunction and just have conjunction and implication, then it's decidable. If we restrict to persistent valuations, then we accept negation-free intuitionistic logic, which is also decidable. And so on the one hand, there's something that seems to say we're close to the decidability area, the realm of the decidable. But we also know it's very closely related to the standard of relevant logic R, and in particular, it's what people call this positive fragment, but it's essentially just negation-free. And that is undecidable. That was proven by Urquhart in '84. But in it, S eluded these techniques, so he proved R undecidable, but not S. And eventually, this led experts, including Urquhart, to consider that S is decidable. So this is what we know of the problem beforehand. Now we have some insights. Let's see what do we notice about the problem using these insights. So first we had the thing with evaluations. Valuations here are arbitrary. So this thing with maybe if we take 16 valuations only, then we get something that's decidable. We don't really care so much about that because we saw this exact phenomenon before, right? With team logics, so these principal downsets is also a notion of being persistent. That these here, there we were decidable, and as soon as we allowed for arbitrary evaluations, we got undecidable. So suggesting undecidable is perhaps a bit of a strong word, but it's essentially that at least we can disregard that point. Then S is negation free, which might suggest decidability. And then we had the last thing, this notion of associativity. So the frames of it are similarities, and they are indeed associative, which suggests undecidability. So by majority voting, 2 undecidable against 1 decidable, this is undecidable. But let me say one last thing actually, is that when I was thinking about this, guided by these insights in the sense that I was thinking, okay, so we might not have a negation, but there is residual, so the implication here, even if it has no bottom, it sort of behaves negation-like. And could I somehow try to extract that? Because I knew I could tick off the other boxes that I knew made for decidability. I just had to tick off this last box, sort of, at least heuristically when I went about it. So I was trying to use how can I use the residual in some way to sort of get negation. So it's actually not only just something I'm saying, like it was really insights that were valuable to this. This paper is published. You cannot see the reference here, I think, but it's not important. So how, I think I won't cover the proof, but I can say a bit about, well, let me say, so I'll give you a guide to the paper. So the proof of its undecidability is quite convoluted, but there's a way simpler proof, which is just that it doesn't have the final model property, and it does illustrate some of the same key ideas. So if you're interested, like guide to paper, read the FMP, like no FMP proof. That one is very simple, actually, and still you get some of the same insights. So I'm not gonna. So you have the formula actually in the handout, but I think I won't cover it here. Okay. So this is the logic. Yes.
Can you remind me the relation between the final model property and decidability?
Yeah, so it sort of depends. But if you have, so for instance, what you have the following. So whenever you have a finally axiomatizable logic with the final model property, then it is decidable. Because what you can do then is that you take the final models that define it, and then you can, for each of them, you can since only find many axioms to check. Or you can actually you don't even have to say what the final model, don't even have to be recursively enumerable, the models. Because what you just can do is that you can enumerate all finite models, even those that are none of that. And then you just check which of them satisfy the axioms.
Yes.
And then you check for it. And all of this is like finite things you only have to check because it's final model, only finite main variations. There are also, if it's a recursively, so this is one result, if it is a recursively enumerable class that you have final model property with respect to, then it just needs to be recursively axiomatizable also. Because the idea is that in general, the finite model property, what it gives you is co-recursive enumerability.
Yes.
And then you just need recursive enumerability.
Yeah, okay. So that's what I thought. So if you have the final model property, then you can prove a decidability problem. But here you said that you're proving undecidability.
Yeah, no, good point, good point. So, yeah, exactly. So in general, what you have, so this implication is a suggestive implication or something. It is not that FMP implies decidable. So this is not true at all. If you have to read of it, like sort of, you can use FMP
You can use that
for
yes,
this,
yes.
right? But that doesn't say anything about that you can use no FMP to get undecidability, right? You don't get that. But oftentimes, actually, the links are quite strong in both directions. So oftentimes you can use no FMP to sort of like suggest even weaker than this here, even weaker form of implication, suggest undecidability. Yeah, but no, good point, good point. Okay, and then, okay, so this was the logic S. Then we could be thinking, okay, what about this relevant logic R that is related to? So we know that Burkhardt, when he proved it undecidable, and also other relevant logics undecidable, he concluded by remarking the undecidability results omit one notable case. This is the logic consisting of all formulas valid and similar to semantics. That's the logic S. The decision problem for this system is still open. So this suggests the following question. Now we have a proof of S undecidability. Can we extend this to cover R as well? And actually also E and T that you also showed undecidable. Yes, it does extend to even to R plus, which is a reduct of it. And if you're undecidability in a reduct, you also need greater language. Now I said 2 comments to the proof. It will be very brief comments because I think they will be, but if you're interested, I can always talk about this later another time maybe. So one is that I use a slightly different tiling problem to make this work actually. And the other here is sort of a suggestive idea for how it is that in general, this notion of associativity, how it relates to tiling. I won't go into it now, but there you can really see like visually like see how associativity relates to the notion of confluence actually of the tiles, but not so important. Okay, so those of you who have read the abstract will know that the last thing I talked about was the abstract of this talk was these problems here. And also, if you recall the plan for the talk I put in the beginning, what I said would be the last thing was that using insight to solve one last problem and provide a new proof of an old result. But the abstract was outdated. Okay, so maybe the plan for the talk was not outdated, but it was lying a bit. So it was one penultimate problem. Because when I came here, as Peter also alluded to, then we were like discussing, brainstorming about what kind of problems could we work on while I'm here. And then Peter mentioned this problem that, so it's called bunched implication logic. And he mentioned, okay, so there has been multiple proofs or claimed proofs of decidability, but Peter and others, Ravantha and Ramanayake and Galatas has found gaps in these proofs. And now I was actually thinking, okay, maybe actually it's not decidable. So let's give it a try. Let's settle out. Let's figure out if it's decidable. Let's finally prove it. Or let's also try thinking whether it actually is undecidable. And what logic is this? This bunched implication logic? Well, so the question is bunched implication logic decidable? And the way you can think of it, so let me give two ways to think of it. One is that you take intuitionistic logic, and then you add this notion of like the fusion, the circle we had before, and of the implication from relevant logic to it. That's one way you can think of it. For the algebraist, think of it as residuated Heyting algebras, which sounds perhaps a bit weird because Heyting algebras are already residuated. But what I mean is take a residuated lattice, take the lattice structure and assume this one is actually a Heyting algebra already. Then you almost have BI. If you assume commutativity also as the last thing of the fusion, then you have BI. Okay, and question. Is it decidable? Claim decidable before? As of last week, proof, no, it's undecidable, actually. So let's end on this note. So here's the conclusion. So we obtained some new undecidability results. So we had this modal logic of Boolean algebras, output modal logic, also of similar lattices. Is this undecidable? We also got another proof of this very nice result by Urquhart. A very nice proof also he gives. So then we have BI to be undecidable as well. Then we compared them with decidability results to try to carve out this boundary. And where we had propositional team logics were decidable. We had modal information logics decidable and truth maker logics are decidable. And this leaves us with these core messages, which is that for decidability and undecidability, valuations matter. That's propositional team logics comparison. Associativity matters, comparison with modal information logic, and negation matters. But in fact, right, in the relevant logical setting, we didn't really have a negation. So the way to maybe put it for now is that we only needed a tiny bit of meta language. It's not the case that tiny bit of that to get undecidability, at least in some settings. This is the conclusion. These are the core messages. Here are some of the references. Thank you so much for your time.
Okay, we have questions.
Well, I have a question. It's a wonderful talk. I like it. It was very well, organized it, very well explained it, and very nice. My question is, oh, sorry.
No.
My question is, can you extend these results on the already hand off the toy, the quite like it, not to undecidability, but to incompleteness of modal logic? Like it. Did some work on that, and Van Benten did some work on decidability. It looks like the stage is ready.
Yeah.
My impression.
So you're thinking of like Kripke incompleteness logics.
Yes. Now you'd be like it hyper Kripke because you are using the Turner relation. Anyway, but that's okay.
Yeah.
Using this Turner relation, I think the stage is ready for obtaining a result like that.
So I think, there could potentially be some there. I think in general, most of these logics are sort of complete by definition. Because what you define some of these logics, right? So if you take the one on similar, this is the where you algebraically you take the variety generated by complex algebras of similar lattices. But modal logic, what you do is that you simply define the logic to be the logic in the, so you give the cryptic semantic clauses, and then you just, as you would do, but where the structures you're interpreting them on are defined to be similar lattices. So this logic, so what you have here, right? So the modal logic of similar lattices, we would call it this one here, right? Is, and this is so it's defined to be. Oh, actually, let me write it all a bit on. So it's defined to be the logic of a class of frames already, class of cryptic frames. So this one, for instance, it is actually cryptic complete by definition. And this is the case with more of them, that there will be cryptic complete actually by definition. But there could be some interest into some of these things that we're looking into cryptic incompleteness. It reminds me of another problem I will tell you afterwards that I mentioned to Peter also the other day, which I find very interesting. Notion of like this is within the intrusionistic setting, so hitting algebras. But I'll mention that afterwards because now it's a bit an aside. But I think if you're interested in this cryptic completeness and completeness, you will also find this problem very intriguing, I think. But I'll mention that afterwards, not because it's sort of an aside.
Okay, good.
But thank you so much.
Thank you.
Other questions? Peter?
So this generalizing the valuations to, so allowing all valuations makes it undecidable. But are there some smaller sets of valuations that are not just the persistent or the downside valuations that still give you decidability, or that would be interesting in some applications?
No, I think it's a very interesting question. I think so. My guess from looking at the proof is that what you need was essentially, right? So we have this notion of persistence, and what persistence this allows is that we can flip sort of like if something satisfies the proposition that now, it also do it below. This seems to be quite important because when I encode the tiles and stuff like that, then as soon as if it's persistent, then as soon as I say, so I encode these tiles as propositional letters, as you know, then as soon as you say something satisfy a tile, if you have persistence, it means that everything below you also would satisfy the same tile. So what you need somehow, you need some sort of at least periodic possibility of jumping to something that is different.
Yes.
But this is my intuition extracted from the proof. I don't have any results that show like this is the exact restriction you need. But from the proof, this is the intuition where it's important.
So could you say a little bit more about that? You said periodic, that's very suggestive. Could you just say a bit more?
Yeah, maybe not periodic, but at least what you just need to be able is you need to be able to keep on flipping somehow, in some sense. So it could also be aperiodic. I don't know, but you need to be. So maybe it's a bad choice of word. What you don't want, because okay, so I can maybe say this: when you have this notion of persistence, the thing is that when we encode the tiling problem, given a set of tiles, we construct. Wait, let me use black. I think that's better also for the Zoom audience. So if there's an audience, but we do something right. Whenever we are given a tile, part of it is that we construct a formula. This formula here, or no, this is a set of tiles, right? We construct a formula. This formula in it contains sort of because this here, right, is just by definition a set of some tiles. It's called T1 up to Tn. And this one in here contains sort of as formulas these tiles in some respect. Let's just say it contains T1 as a formula, something like that. Then the problem is that we want to assign tiles. So when you have this refuting or satisfying model, you want to somehow say from that you can show that you can tile the plane, tile the quadrant. Then the problem is that, and the way we do is we find within our refuting or satisfying frame, we sort of find the interpretation of how to tile the plane. And then the problem is that if we find within it, so we find this point in here, and this point in here, let's just call it X, it satisfies the formula that corresponds to, let's say, Ti. Then if we have persistence, then if I want to find some other points, and this X here, no, let's call it something else. Let's actually call it n, and say that somehow this is the way we want to interpret the plane in it, right? n natural number. We want to interpret it, and this sort of saying that this point here, or the corresponding point of the plane, is supposed to satisfy this tie here. but this we find it in our frame if we have persistence. It means that everything down here. So if we wanted to find, maybe we want to find m plus 3 and n plus 2 down here, but by persistence we cannot say anything about it having to satisfy another tile. And suddenly you get, well, you also satisfy the same tile. So what I need somehow is I need to somehow be able to, at least if I'm going in this direction, if I'm trying to interpret sort of the whole plane going in this direction, persistence is for the proof strategy I have would like destroy. This is how persistent, how I can see from a proof strategy why persistence makes a difference. So what we need somehow, periodic is probably the wrong word, but we need to somehow be able to flip. We need to be able to say somehow at some point, at some point down here, at some point, maybe we can flip.
Is phi a conjunction?
You have it here. The formula here. It's a conjunction. In one case, and the other, it's an implication. Yeah, thank you so much.
Yes, so I have a question. So you are speaking about a logic as a set of formulas,
Yes.
typically the set of theorems of, right? But there's this other notion of logic that is the implication, I mean the consequence relation,
Yeah.
right? So is there any way that these theorems could be lifted to the consequence relation, not just the set of pathologies?
Yeah. So you get if it's undecidable. So if you have so the consequence of the difference is whether we're considering this relation or whether we're just considering like this relation, and this is the empty set, right, as a subset of it.
Yeah.
So if this is undecidable, then this is undecidable.
Yes.
In all the cases we're considering here, so when people talk about decidability here, they always talk about gamma being finite.
Yes.
And then the thing is that if gamma is finite, and if you just have conjunction, then you can take the conjunction, and if you have the deduction theorem, write it over here, and then they're equivalent to each other.
Yeah. So actually, yes. So my question really was, do you have deduction theorem in this? Any kind of?
And then but what is perhaps interesting is that I also mentioned truth maker semantics, and in there, the way I phrased it was, so for those who are actually familiar with it, it would maybe look a bit weird because I phrased it differently from what you're used to, but I hope that's okay. So this was the signature. Here you don't have the implication, so you can't have the deduction theorem. Well, potentially you could have it for some combination of these, right? But you don't have, so here you don't have the deduction theorem. But the notion of decidability in truth maker semantics is actually not in terms, is not given in terms of this here, because this here would be easy, because truth maker semantics has this many theorems. There are no theorems, so it's very easy to decide. So instead, it's given in terms of this here. And then it can't be translated into this. So there's actually, so when I talk about truth maker semantics,
It is
actually what I was talking about was this here, but where this here is finite. Yeah. No, good, thanks, good question.
But if you have a kind of compactness, then you can even make it larger.
Yeah. Then you can say at least no, not really, right? Because compactness is
absolutely decidable. Right?
Yeah, the compactness exactly, because compactness would only say that from this here, right? What you can conclude is that there exists, let's call it gamma f, subset of gamma, and that gamma f is finite, such that gamma f fine. But if you just present, let's say you only just presented this somehow, right? How do you find this gamma f?
Axiom of choice.
No, but it has to be the truth machine has to be able to. It has to be able to.
Under
encode
the
it.
assembly.
You first use an article, and then you have the decision procedure.
That you can do. That way you can also solve the holding problem. Just start with the oracle.
Those are the axiom of choice of this in computer machine.
So why is decidability, as you said, it's a deep and profound problem, and we don't need to distinguish, but why is it either deep or profound, or both?
No, for me, it's this idea, right? I found that it's more like the conceptual distinction between things that are decidable and undecidable. So this we talked about also with math. I put it maybe in an extensional way, but think of it intentionally. So it's really just the concept of a conceptual distinction that I find to be very deep and profound. which is like whether a problem admits, like has this algorithmic content to it, admits like this mechanical procedure to be solved, or whether it doesn't, whether it falls outside of that. I just find this in and of itself, like, it's sort of like, let's say, finite versus infinite. It's sort of like that. I find this to be a deep and profound conceptual distinction, right? It's the same sort of idea. At least to me, right? I think this is somehow intrinsically, this is very intriguing.
But the very notion of undecidability, the very notion that there is something that is undecidable, I think this is already very, very profound.
I agree.
Because you are saying there is this problem, and it's not that you are not smart enough to find a solution, it's that the solution doesn't exist. And it's one of those like Galois theorem that you cannot find a formula for the quintic, the Gödel theorem that you cannot prove the consistency. It's one of those notions, right? That, it's a limit of, it's not a limit of our imagination, it's the limit of
of thought in some sense, right?
Minds cannot.
Yes, but this is not only a conceptual point, because in order to do it and to give sense to the idea indecidibility, you need to have a meta theory in which you can prove something about the theory. So the question is not only conceptual. So I have a student that makes a PhD with me on the origin of the notion of impossibility. So when the notion of impossibility appears in mathematics. And one of the things that appear clearly is that in a way or another, the notion of impossibility arrives when I have some sort of meta theory. I have a way to translate an internal question in external question. The example of Galois is typical. Of course, Galois is not meta theory in the sense of him, but Galois invented group theory in some sense in order to speak of another theory. So that is the question. You need to have a theory on the theory.
This I think Soren put it yesterday very clearly when he said that if you have just the problem of okay, can I decide? This is very difficult to answer, right? But once you make it mathematical, then you have all mathematics at your hand to prove it. James?
I thought that the no finite counter model part of the result was very interesting. But and so how big is the gap between the no finite counter model property and the full undecidability?
Unfortunately, like it depends. I think conceptually the gap is perhaps not that big, but technically it's huge. Like so, the proof of the no FMP is at least when you implement, like when you see that you can read it and understand the proof, I think very easily. While the other one is very complicated, unfortunately. But I can maybe say a bit about like how is it that they actually connect it? Like how does it? So in the no FMP proof, then one idea that is used here, which I think is also good to emphasize in any case, because I think it's it pops up in many proofs of something having to be infinite, and that is the notion of parity. So essentially, I use some notion where you have something here, let's say E, and then I construct something O. So this is very simple, right? But it's also just to sort of convey the idea. You can just think of this as natural numbers. You have even, odd, even, odd, even, odd. Essentially, I somehow encode this to get the FMP or no FMP. Then the idea is that, okay, so that means you can think of it as I can construct an axis. So so we want to encode the plane, right? Now I have sort of an idea how I can construct like a straight line. So this you can just think of as, okay, encode this once, you get the y-axis. Encode it twice, you get the x-axis. And then what you can then from that see if you can get the full plane, because you have to get sort of the full plane to encode this sort of like the tiling. And then the idea is that so you want to construct it twice, and what you do, sort of one idea is that you cannot just construct it twice. It's a bit more complicated. But what you think of is here we are working modulo 2. What if we work modulo 4? So right, so what we have here is that we have something that is 0, mod 4, and then we have something that is 1, and we have something that is 2, and 3, and then we go back to 0. So at least this is the way to think of it, right? Because if we do this now, and then we repeat, then we go back to 0. So essentially the idea is that take the idea, so one idea that sort of extends is that you can think of this sort of parity idea that gives you sort of the infinite structure, and sort of like giving you one axis. And if you, instead of thinking parity, you think mod 4, then you can kind of get both axes. It will look a bit different than just getting both axes. That would be amazing, right? But this is the sort of intuition, I think. Or at least one of the intuitions that connects them. Oh, very good question, James. Thanks.
Well, because, I mean, certainly there are order theories that lack a finite model property, but are still decidable. So there's something, the fact that finite countermodel, the failure of finite countermodels is sort of a stepping stone toward the undecidability. There's something specific happening.
Yeah,
in the meantime.
It's sort of this idea, right? That we can, at least this is part of the idea that from the no FMP, we can sort of think of this as essentially what it establishes almost like getting one axis. And then we extend this result to get both axes. This means we can essentially interpret the whole plane. And then we have to do some more stuff, but then we can start tiling. But yeah, what do you say? So if we take, for instance, monadic second order logic even, right, is decidable. And it doesn't have the FMP. The monadic second, what I mean is monadic second order logic of trees, right? But because it's defined, so it's important I said that, because otherwise what I said was very wrong. But, of trees, so even of infinite trees, so the infinite binary tree, for instance. And that one doesn't have the finite model property. But this is something called also oftentimes the tree model property. Because trees are sort of, you can use these ideas for like automata and these things. They're very computable somehow. But notice, right, that the distinction between trees and the structures we are talking about is the trees. They're sort of like, let's take the infinite binary tree. So, omega. So it looks like this here. And goes on. But this here looks very different, right? You have no confluence here, right? In our case, what we're talking about when we have similarities and stuff like that is that then we have things like if you have a point, so let's suppose we have this here. Suppose you have a joint similarities. From this, you know that this point here must exist. So you're really getting out, so to sort of say, this is maybe another conceptual point. So even in such a strong language as monadic second order logic, incredibly strong, even in such a strong language, when we interpret on trees, we actually have decidability. And sort of the distinction, we have extremely weak languages compared to, but our structures, in particular, they're really not like trees, right? They're really like, they can have these confluence properties. That maybe also can sort of give you some intuition of why is it that in such strong language we have decidability, while in so weak languages we have undecidability. This is at least some intuition to it. No, and so also what I want to say is we were talking about finite model property. I think that what I also want to say is this notion of the tree model property, which this also kind of illustrates, is extremely important. Like so final model property is oftentimes heralded as the most important, but there are people who are arguing that actually the tree model property captures decidability in a way better way, at least in some instances. Okay, that was maybe a long aside, but thanks for the question again, James.
Maybe just to comment, the interesting thing about BI is that it was developed as a propositional logic of a Hoare logic called separation logic, and in computer science it was deployed to talk about concurrent processes very effectively, and it was hoped that it would be decidable because then it could be argued that this is absolutely the right logic in which you do this type of verification. Now it turns out to be undecidable, which is very interesting. It's still a practical logic. Separation logic has already proved its value, but it's nice to have resolved this theoretical question.
But it's also interesting that there were wrong proofs for quite a long time about BI. So it seems to me that you're right on the boundary here.
Indeed.
Right. So Right, some problems it's quite easy to see that they're decidable, and some it's quite easy to see they're undecidable. But there's this sort of frontier.
No, indeed. This is the frontier that we like. No, this is very interesting. Both of you. So actually, this reminds me of something that we need to check. But with that, Peter and Nick might have a proof that if we change the thing to time, but okay, so let me write everything a bit differently now. Like, do I have time? I do have time still, right? Yes. Okay, sure. So now I'm going to write this all in like the sort of signatures we have been considering. So first we were considering, so this is Boolean algebra, we were considering, and where we had this circle. So this was one signature we were considering. This here, and this here.
Sir, can you stop the sharing, maybe?
Ah, yeah, yes. Yeah, good, good.
Oh, for him, logic is just a set of formulas.
So we have this here, right? And then we have, let's see.
Look, it just means it's in. That is a set.
Then we have this here. Now I'm going to write it, so we had this notion of implication, but because it's going to be confusing if I use the same symbol, this is the residual, so I'm going to write it like this here instead. But this is the relevant one. So here we have, this is like modal logic. Modal logic. Here you have relevant logic. And here you have BI kind of logics. And okay, and let me see, and over here, so, and then here we also have square increasingness. This is a distributive lattice. Residual. Then you have BI. BI is actually, so the whole language of BI is quite long. So it's like, and I probably will forget something now, because it's very expressive. So the heading algebra, so that's why I use this simplification now, because it's different from this one over here, so not confuse things. So this is a heading algebra, this part of it. And then so we have intuitionistic logic, that's it here, intuitionistic logic, and then you add these here. So let us just, I'm just going to add both residuals here also, even though they work on it slightly differently, but I think it makes it easier. So they have not right here. So people use sometimes this here, or sometimes this here, and they collapse because you have commutativity. Then you also have this here, and I think you even have another notion of a top element, like an identity, just an identity for this here. So this here is, so what you have here is your heading algebra, and then you have over here what do you call this? What do you call this?
Residuated lattice.
It's residuated lattice. I mean,
so you say this is the other part, and then also with the identity also here. I just write it like this. It's not entirely correct. Okay, so what you were asking also, Drew, and that's why it took me some time, but I wanted to put up all of this a bit, is that BI looks like this. But actually, for undecidability of BI, all we need is, we don't need, this one we don't need at all. We don't need fusion. We don't need bottom. We don't need top. We don't need implication. All we need is just a tiny bit of negation. And we don't even know exactly how weak this negation is, but it doesn't even need to satisfy double negation introduction, not elimination, double negation introduction. So this here is already undecidable, but if we, and this is, so this is already, so the undecidability result already in this. So if you're undecidable in a reduct, then when you add more language, you're still undecidable, right? Because you can't even decide the formulas in this fragment. Mm-hmm. Then there's another thing here, and that is that, so Nick and Peter might have, this is to be checked, so this scheme and everything here, a proof that even, so if you take the full heading of the graph here, so we even go stronger than the undecidability here, but instead of having the residuals over here, you have the fusion. And I think you can even also have, I think, the identity in these things, that this here might be decidable. And which is interesting also, right? Because when you look at it, what you have here, right, is the heading algebra. plus this sort of fusion. Up here, if we have Boolean algebra, so, and this is Boolean algebra plus fusion, we are undecidable. Potentially, if we weaken, in this case, from Boolean to Hagen, we get decidability. This is to be checked. So it really seems we're really on the frontier of decidability.
But it's still, even if you don't put the residuals inside, this fusion is still residuated.
Yeah, we just don't have the language to
Have the
talk about
language
them.
to talk about the residuals.
Exactly.
It's like a quantile style, but it doesn't have to be completely there, right?
Yeah.
So
So can I ask a very fundamental question that shows that I understood nothing of your talk?
Yes, please.
What does it mean that a formula belongs to a logic for you?
So in these cases, it depends on how it's defined, right? So if you define your logic, so maybe you can have this here, right? So here you have defined it in terms of the, so there's something here that's missing, right? Similar. Yes. So the way here it's defined, right, is you, in these cases, you were given a set of structures, right? So we gave the semantics. Here, in this case, we gave the semantics. So you say, what are your frames, similarities?
So
How do you-
a formula belongs to a logic, whether if it is true in a model or in a set of model, or et cetera, et cetera, et cetera.
Exactly. But typically you have soundness and completeness, so you can also prove
Then,
theoretically.
if that logic is complete, this also means that it's probable. Okay.
Yeah, exactly.
But if the theory is not complete, what we have proved is the semantic decidability, that is not necessarily the same thing that the syntactical decidability.
No, but you wouldn't. I wouldn't say, I'd say if you don't have soundness and completeness, then it's not. Then the two. If you want to give a proof theoretic presentation, right? If you don't have soundness and completeness, you have the semantic representation. They're not presentation of the same logical systems, right?
Sorry?
Then if you don't have soundness and completeness, and here you have a, let's say you have a proof theory here, you have some semantics or some model theory here, but they're not soundness and completeness. Then these two are two different logical systems. Right? It's only so what? So then,
Second order logic is sound, but it's not complete. So it's not.
it depends on what the axioms you give, right? Can you give? Oh, I don't remember. I think you can give these weird things.
soundness and completeness is always a relation between two logics, and when it's sound and complete, you are saying the two logics are the same. When that's what sound.
No. Repeat.
Soundness and completeness are theorems that say this logic and this logic are the same.
Exactly.
Yeah.
You know, a very interesting point, because there is no difference between syntax and semantics in a sense.
That's what they show,
Yeah,
right?
that's
Which is the
right.
beauty of it.
This is exactly. This means that there is no difference between syntaxes and semantics.
What this means is that you can present the same logic semantically and syntactically. You have
Okay.
two ways of
Now I
presenting
see
the
what
same
you mean.
logic.
And which is beautiful also, right? Because if you think of it, this
Yes,
notion of
but there are, it seems to me, a large family of logic, call it, that are not complete. Are not sound is a little.
There are
not
many
complete.
logics that are presented semantically and do not have any syntactic counterpart. There also could be also logics that have a
No,
syntactic
it does not
presentation.
mean that I have syntactical counterpart. I mean that I have not a procedure of proof. In second order logic, I have a syntax and semantic. The two does not coincide. What does it mean? That I have a procedure to decide whether a logical truth is the theorem.
So you have two different logics. One is presented
That is totally arbitrary to say that we are different logic.
No,
I have a logic that is not complete.
no. Okay, so no, actually, you can give a proof theory for second order logic. Will just not be. You can give a proof theory for second order logic. Will just not be recursively enumerable, right? And this is typically what
I am not a decidable process of proof. Of course, I can give a proof, but I cannot prove anything that is true.
It depends on what you mean by proof, right? You can give non-recursive actualization of second order logic that you can do. It's just not recursive. So typically we want it to be recursive our axiomatization, right? Our proof theory, but you can give non-recursive.
Otherwise, you can't even tell what is a proof. That's the.
Yeah, these are if you want to have a notion where you can tell what is a proof. And if you take this as a necessary criterion, is that it's recursive, like recursive optimization. If there's a necessary criterion, then you can only tell what is a proof, but then you cannot tell all the truths, right? So you have to. So if you think what is a proof, if we say this is the same as saying our proof theory is recursively enumerable, then that amounts to saying that then we either can tell what a proof is, but we can't prove all the truths, or we say we can prove all the truth, but we don't know what a proof is, and we're in this sort of dichotomy. Right. But okay, so let me see if I can recap a bit and get a bit back to your question. So for me, in all these cases, I think all of the logical systems that I've been considering, they have, like, they're sound complete. They're proof theories which are recursively enumerable, and there are semantics for them. Which means, this is the point, whether I construe it this way, in terms of the semantics, or in this way I mean in terms of the semantics, in terms of the model theory, or whether I haven't written some proof theoretic rules for it, it's the same. The decision problem is the exact same when you have soundness and completeness, and in all of the logics considered here, we have that.
Okay.
Yeah.
So I could construe it either way. So here's this is my notion of like validity of being part of the logic. No, actually, for me, it could be either notion, because we have soundness and completeness. I don't have a notion. For me, because I don't need to make a choice.
Well, for instance, the notion of a consequence relation does not say clearly if you're working on the syntactical side or the semantical side.
If you have soundness and completeness, yeah. You know, strong completeness and strong soundness. Yeah. No, yes, my answer is that actually I don't need to consider model theory. I can consider proof theory.
All this is very, very, very Platonistic.
No, this is not Platonistic. If you have
This is very Platonistic, and it's quite strange that someone like you is accepted this point of view. Very Platonistic.
What's Platonistic about it? No.
Of course.
I'm glad and happy to be.
But it's possible, it's very possible, we are human beings, it's very possible that we are in a situation in which we are able to do something and not other thing, and we try to live where we are. So to say that a logic is to be sound and complete in order to have a logic, it seems to me.
No, he didn't say that at
No,
all.
no one has said that.
No. Soren certainly didn't say that.
No,
He said that the examples that he's dealing with he has a semantics with respect to which the proof theory is complete, so he no longer cares which way you present it.
Exactly. All of them, this happens here. And my question, right, is this so in all of the cases, all of the logical cases, all the cases I consider today, this here holds.
Yes, if you have soundness complete, one is the same.
Exactly.
Okay.
So for me, the problem.
But the interesting case is when we have not that. This is my point.
Yeah,
This
but
is
those
when it
I'm
is
not
interesting.
considering. But those are.
When you have not.
I think those are in general those are undecidable by definition. If you take this definition that a proof theory has to be recursively enumerable, so if you don't have soundness completeness, then by definition they are undecidable because they're not recursively enumerable. And then there's no question. So I would actually say, you say the interesting case is when you don't have soundness completeness. I would say that's completely uninteresting because there it is by definition undecidable because by definition it's not recursively enumerable.
We could have a logic presented syntactically, recursively enumerable. I mean, the fact that it doesn't have a semantic.
True, yeah. What am I talking about? You're right.
The fact that this doesn't have a semantic doesn't mean that we cannot ask the question whether this is decidable or not.
Yeah, it could be exact. No, you're right. Indeed. So you could have a logic that is not recursively enumerable. No, but then you don't have this here, right? Then you don't. Yeah, but the question of this decidable is still interesting because.
Exactly.
Yeah. Now let me backtrack on all of that. Right.
So there's this point that people speak about: is this logic sound and complete? This question doesn't make any sense because you have to say, is this logic sound and complete with respect to this other logic? So one logic cannot be sound and complete
by itself.
The sound and completeness theorem is those are theorems relating to logics. They are saying you can interpret this logic inside this other. You can interpret this other inside this logic. They are going to have the same theorems or they are going to have the same consequences. But this is sound and complete.
Typically, you will call this direction soundness,
Yeah.
and this direction completeness.
Okay, that's of course. Okay, this is always my problem. According to me, what is on the left is not logic. The only thing that interests me is what is in the right.
Okay.
But then it's good.
Syntax is
We have this-
impossible. Semantic for me is a mystery. That stranger Platonist people that begin to think that we know what does it mean to be true. I don't know. I have no idea what does it mean. It's completely. I do not see. For me, it's
If you want to know if something is true, just ask me, and I will. tell you.
okay. I ask you, and then you tell me.
No, but the good is in these cases at least we can be all over here where you think here's logic. Here we have
Sorry?
logic. In all of the things we consider today, we are in the camp where we can present it in terms of derivability purely.
But if they are saying that is the same thing.
Yeah.
If you have
Exactly. Yeah.
Is another way to put what makes this interesting for you, and it may not be, that we can ask what things are knowable by any means whatsoever, and what things are completely, absolutely unknowable. We can also ask what things are knowable by certain means. So humans discovered a kind of tool, which is effective decision procedure, or effective mechanical procedure. And this tool can do so much, it's incredible. This set of tools can do so much. But then they can't do it, they have some limits.
But they can do
Try
so
to-
little. I would even
Well,
say. Surprisingly little.
I'm
You would
glad
expect them
that-
to be so much. No, in some sense, a lot, right? Like computers, they can do everything, right? Somehow they can record me now and put me on the screens, right? How are they doing that?
Yeah.
But no, yeah, true. So they can do so much, but they can also, in some way, they can do so little because there's so many things that are undecidable. But yeah, I think that's a good way to phrase also what I find interesting. Yeah.
And so, I mean, there's some things that are undecidable. But then you're sort of interested, it seems to me, in like, where exactly is this boundary? That's very.
Yeah, because I think that's if you really want to understand this notion of this concept of decidability and this concept of undecidability, it seems to me that the way to really understand it is understand this boundary to the extent that you can. Right, because just taking something that sits like very firmly within decidability and like, okay, what then do you gain of understanding, right? You need to understand this border.
It's unlikely that that's a decidable problem.
It's an undecidable problem. It actually is. So you have these results on even if you take logical systems like finally presented logical systems, it's undecidable whether they are decidable. So there's this meta notion of undecidability also going on here.
Then that allows more creativity.
Maybe yes, yeah.
Okay. Is there another question? Objections?
No, I have a question for you. It's necessarily only for you and Drew, but we can discuss now. What we are doing with Euclid,
Yes.
what is the semantic of what we are doing with Euclid?
Are you asking me for the semantic?
We are never interested in this. There is no semantic.
I don't think there's any.
I don't think so.
I don't need any semantic for what we do.
No, of course not. No.
Just a purely syntactical word.
A purely syntactical thing, yeah.
So
Wait, isn't Euclidean space a semantic
Nope.
notion?
Well, sure it is, but that's not what we're talking about.
It should be in principle.
We refuse to talk about it, but I think Euclid was inspired by it.
Well, this is a discussion that you could have with
that is another story.
Marco.
That's another story.
But I guess Euclid's
Another
logic
story.
is sound with respect to Euclidean.
It should be
geometry,
sound
right?
with respect to
Yeah.
Euclidean space.
But it's
Sound,
probably
it should be sound, yes.
Yeah, sound, but not complete.
It's probably not complete,
No,
but quite
very
certainly
far-
not
I think
complete.
very far from being complete. Yes.
So you have semantics, and Euclid, like you haven't developed, right? But here are some semantics that at least the sound.
We get semantics. Yeah.
And Euclid was interested in semantics, right? Because you were interested in geometry.
That's a maybe.
Otherwise, you would just do chess rules, right? Only don't just do chess rules and like give the syntax for that, right? He was actually interested in the semantics, which is whatever it is, right? And one could be.
Yeah, but the question is, did he have in mind a plane in which all of these things are living? And that seems clearly not.
But, so Euclid was not a
He was-
Platonist.
No,
Euclid was not a
Platonist.
Oh, certainly not.
No, he wasn't. So, because all of what he says has to do with figures, individual figures. That's all. That's it. So you don't need quantification over planes and points in planes, and you don't need to imagine that a segment is an infinite collection of points.
Oh, no,
None of that is none of that.
Yeah.
None of that it would. I don't think even would have occurred to him to say.
Difficult to know.
In any case, the point is not Euclid. My point is not Euclid. Euclid was simply an example. It's an example of something where we are working from 3 years in identifying a syntactical system. And nobody between us even added a large idea to construct a semantic. Well, because the identification of syntactical system seemed to be a very interesting.
Yeah,
Yes.
I think that I think mathematicians try
But
the
it
syntactic
is like,
thing.
my impression is that mathematics is that. It's the construction of syntactical system.
But this is
But
this
the
is not what,
semantic of mathematics is not mathematics.
This is
It's
not what the mathematicians
the
did.
preoccupation of logic, not of mathematicians.
some mathematicians like Hilbert was interested in the syntactic thing, but what the rest of mathematicians did was the semantic thing, was constructing Euclidean spaces. That's the semantic.
But you're
And,
right.
and this is what mathematicians have been preoccupied.
And what a
with
mathematician
Euclidean
is
spaces.
interested in is to prove a theorem, not to know whether it's true or false.
You can prove a theorem about.
Tarski, definition of truth by Tarski.
Tarski was not a mathematician, was a logician.
But the vast majority of mathematicians work semantically. They have
Yes.
no clue about syntax or
Absolutely.
correct proof. They don't care. As long as it's
Yeah.
true in the real
That is
line.
called informal mathematics.
No, it's just mathematics.
This mathematics.
That's what Peter's describing is mathematical practice. That is what people do.
You are reducing a mathematician to a geometrician.
Do we have any more questions for Soren?
Okay, that's another story.
Okay, then thank you.
And thank you so much for all of your questions. It was a pleasure.